So if I give you a parabola or a quadratic function, right, whose graph is a parabola, how can we find the vertex? Remember, just so we're all on the same page, the vertex for a parabola that opens down, that's the highest point. For a parabola that opens up, it's the lowest point. Right? And this is really kind of a big deal question. And in a practical situation, that vertex is the maximum value or the minimum value that whatever it is you're modeling takes on, right? Maybe it's the point where your costs are at their lowest. It's the point where the pressure on a system is at its highest. It's the point where the temperature is at its lowest, um, and that's usually a pretty important point to be aware of when you're modeling some kind of physical situation. So, how can we do this? Well, what I want to do here, and what we're going to do in this lecture, is derive a formula for the vertex based on three things, based on those numbers A, B, and C. Right. So to do that, I'm going to start with just very generic y equals ax squared plus bx plus c version of a quadratic equation. And what I want to end up with is x equals some formula in terms of A, B, and C, right? Where x is the x coordinate of that vertex. It's where the uh, vertex occurs. Okay, to do that, I'm going to have to do a little completing the square on this thing. Right, so I'm going to start by factoring the a off of that x squared. Because remember, to complete the square, you can't have, you have to have a 1 in front of the x squared. Right? So if I factor that out, so when I take that a out, right, what I'm left with inside the parentheses is x squared plus b over ax. Right? A times b over a is just the original b. Plus the c. I really don't care very much about the constant term. Right? That part is mostly just going to float along for the whole derivation here. So now remember, to complete the square, I have to take that b over a, divide it by 2, and square it. Right? So if I do that, I'm going to get b squared over 4a squared. So that's what I'm going to add inside the parentheses. Remember, to offset that, I need to subtract not just b squared over 4a squared, but I have to multiply by that a that's outside the parentheses. So I'm going to subtract a times b squared over 4a squared. And at this point, this really is where I wanted to be, right? I can factor what's in the parentheses. That becomes x plus b over 2a squared plus c minus, and I just simplify a little here, right? That a can cancel with the a squared. One can reduce the a squared, and it ends up b squared over 4a. Okay, so here's where we have to think about this for a minute. Let's say that a is positive. All right, so this is a parabola that opens up, and we're looking for the minimum value. All right, the only part of this whole thing that I really care about is this first term here, because that's the only part that has a variable in it. Right, so that's the only part that I have any control over. So the only way for this to have its minimum value is for that expression to be 0. Because it can't be less than 0. A is positive, and when I square something, it's positive. So that's going to be a positive number, and the smallest non-negative number available to me is 0. So that vertex is going to occur when the thing inside the parentheses, that x plus b over 2a, is equal to 0. And if I solve this equation, I get my formula. X equals negative b over 2a. Now, you might be thinking, okay, well, what about the reverse case? Right? What if a is negative and the parabola opens down? Same argument works. Right? Same argument works. Now I'm looking for the maximum value, right? And that expression is going to be at its minimum now when it equals 0. Same argument works both ways. So regardless of the value of a, our formula for the location of the vertex of a parabola is x equals negative b over 2a. Now, some textbooks will say, okay, well, what about the y value of the vertex? Well, if you take that, substitute it back into our formula there, that whole first term becomes 0, and all that's left is y equals c minus b squared over 4a. Okay. Not quite as elegant a formula as negative b over 2a, but if you like a good formula, by all means, remember that one and you'll be in good shape. If you don't, look, just find the x coordinate using our formula here and substitute that back into the original equation. Do a little arithmetic on the right-hand side. You get the y value, right? And you don't have to go to all that trouble. So just to be clear, right, I'm saying that the x-coordinate of the vertex is negative b over 2a, and the y-coordinate is given by this formula, or you can just go back to the original equation. Okay, well, one more thing I want to talk about, one more really kind of useful tool that we can get from this. This was the final line in my derivation from the previous slide. If I simplify this a little, I'm going to replace that b over 2a with a single variable, h, and I'm going to replace the c minus b squared over 4a with another single variable, make it k. I get this really simpler looking equation, right? This version of a quadratic equation has a name. It's called the vertex form of the equation. We call it that because you can really easily grab the coordinates of the vertex, right? If you can manipulate your quadratic equation into this form, the coordinates of the vertex are h comma k. And you'll notice, I did fudge a little bit. I changed that plus to a minus. That way, I can say that the coordinates of the vertex are just h comma k. If I had left it as plus, then it would be minus h comma k, and that's maybe, I don't know, a little harder to remember. So we usually write it this way, x minus h and then plus k on the end. Okay, so in the next lecture, we're going to go back to talking about graphing, right? Because being able to locate the vertex is, as you'll see, a really useful thing. It makes the process of graphing a quadratic function, graphing a parabola, a whole lot easier. If you're looking for some more kind of numeric or quantitative applications of this, we are going to talk about that as well as a couple lectures down the line. We're going to have one or two where we talk about optimization problems, right? And this formula will reappear then in the context of some specific applications.